Well, hello there. So we are working on Gauss's law, and we've already seen Gauss's law applied to a point charge, something with spherical symmetry, to a line of charge, something with cylindrical symmetry, and we will do the other two symmetries now, which are a sphere of charge, which still has spherical symmetry, and a sheet of charge. We will calculate the field of a sheet, and see how Gauss's law applied to those two symmetries, those two symmetries on top of the others we've already seen. In all cases, I will remind you that what we find is that when we apply the integral to find the flux, that the integral, there's no actual integration, right? We end up choosing a symmetrical situation such that the field is constant and the angle is constant, so that the integral is just the integral of the area of the Gaussian surface that we choose, and as long as we can find the surface area of something, then we don't have to do any integration necessarily. There are situations where we would have to integrate to find the charge enclosed, but that has nothing to do with the integral for the flux. You'll see what I mean when we get there. So we're going to apply Gauss's law to another situation. Let's start with the sheet of charge. So let's say I have a sheet of charge, and the sheet has area A. Let's say it has a total charge of Q, and therefore it has a surface charge density sigma of Q over A. And we've seen this before when we calculated the field due to a sheet of charge before. And I want to calculate and we know what the field is when we calculated it using Coulomb's law, but now we're going to calculate it using Gauss's law. We're going to make the same assumption we did before, which is that the sheet is large, or that we're close to the sheet so we don't see the edges. Just like we're close to the surface of the Earth so we don't see the edges of the Earth, we don't fall off the flat Earth, or we don't see the curvature of the Earth either. So we're going to assume a large sheet, or that we're close to the surface. When you're close to any surface, it looks flat. It looks like a sheet. And this is actually interesting because what it means is that regardless of the shape of the surface, when you're really close to the surface, it looks like a flat sheet of charge. Just like when you're close to any gravitational body, when you're close to the surface of the gravitational body, it looks like a flat mass, so that the gravitational force is a constant. That's why the electric force near a sheet is constant, because it's flat. So in order to always be close to the surface, or always be not near the edges, we could just make it an infinitely large sheet. In that case, the area and Q would be infinite. Each would be infinite, but infinity divided by infinity is still going to be sigma, the charge per unit area. We would still say there's a charge per unit area, even though we have an infinite amount of charge and infinite amount of area. We would have a charge per unit area. Now, as a reminder, we had already calculated the electric field due to a sheet of charge, and we found that the electric field was sigma over 2 epsilon 0 on either side of the sheet. We know that the field points away from a positive sheet, or if it was a minus sheet, it points towards it. So this shows if the sheet was minus, it still has a charge per unit area of sigma, but it's just the field lines point towards the sheet. So let's go ahead, and I'm just reminding you that we found from Coulomb's law, we found that, but now let's solve it with Gauss's law. And what we will see is with Coulomb's law, in order to get there, remember, we had to do an integral around a circle, and then we had to do an infinite number of circles of radius going from 0 to infinity in order to find the sheet. So it was 2 integrals. With Gauss's law, it's going to be 0 integrals, or one integral that's easy to solve. So here I've redrawn my sheet. I just made a positive charge. And I've also drawn a side view of that sheet, just so we can think about what the symmetry is. Right, the field lines. Think about what's the direction of what does the field look like The field points away from the sheet everywhere, but the field lines don't get farther apart. There is a constant field as long as they don't get close to the edge, or as long as it's infinitely large. So the field lines are sort of like this, but they're all over the place. It gets to be sort of like a really dense forest. Beneath, we would point away, away, away. Okay, so what does that field look like on the side view? It's easier to see. From the side view, it looks like this. But don't be mistaken, don't confuse this with the line of charge, because with the line of charge, the field has a cylindrical symmetry, so if you move into 3 dimensions, those field lines start pointing towards you. But in this case, if you move into 3 dimensions, you move out of the page or into the page, those field lines are still pointing up or down from that side view. Okay, so looking at that side view, the question is what Gaussian surface would we use? What Gaussian surface would we use in order to solve Gauss's law and make the integral easy on ourselves, right? So we want to find a surface over which the electric field is a constant. Well, and not only that, right, because the electric field is constant everywhere, we could go ahead and make a sphere. So there's my Gaussian surface, the orange surface. I might have drawn it, I should have drawn it as a dotted line, really. It doesn't matter, but it's our Gaussian surface, our imaginary surface. The field is constant over that imaginary surface. Well, it actually, it's different on top and bottom, but anyway, it's constant on the top and it's constant on the bottom. So would that be an appropriate surface? Think about it for a second. The field is constant, but something else is not constant, right? In that case, right, my normal vector is there, and my normal vector is there if I choose the normal to point outwards from that surface, etc. And so what is not constant is the angle. So the dot product would not go away. It wouldn't be a constant, and we would have to integrate over that surface. So the spherical surface is not the best surface to choose. So I'm going to go ahead and delete that spherical surface and ask what is an appropriate surface over which the field and angle is constant, or the magnitude of the field and the angle of the field is constant. Hopefully it is pretty obvious that my Gaussian surface should be something that is flat on the top and the bottom, and it really doesn't matter what its shape is on the sides. So we can just go ahead and, well, I guess it does, it shouldn't be curved. So something like that in 2 dimensions. What is that in 3 dimensions? Well, that actually in 2 dimensions, right? Let me just make sure we understand. In 2 dimensions, it's got to be a closed surface. It's got to be a 3-dimensional surface, but I'm looking at the side view. So in those 2 dimensions, you can see that there are no field lines no field lines pass through the sides, and the field and angle is constant through the top and bottom. Okay, so that's the kind of surface. That's the kind of surface that we want. And what is the shape of that surface in 3 dimensions? Well, that could just be a box. I'm sort of trying to show the box passing through the surface here so that field lines just go through the top and the bottom of the box but don't go through the sides. But that surface could also be what's called a pillbox, which is just a cylinder. So we can use either of those geometries in order to, well, I guess we could use any kind of geometry. We could use this geometry. I didn't even think of that, right? We could use any kind of geometry, and just as long as it's got a top that's flat, parallel to the sheet, and sides that are perpendicular to the sheet, doesn't really matter what shape box we use. Let's see why it doesn't matter what shape box we use. So let's go ahead and just call the area of the top of the box A and the area of the bottom of the box A. Doesn't matter how tall the box is because the field is constant as we move farther away from the sheet, so it doesn't matter how tall the box is. Let's go ahead and whether we use the pillbox, the rectangular box, or some other kind of box which has tops and bottoms which are parallel and sides which are perpendicular to the sheet, doesn't matter. It's going to be the same answer. Let's go ahead and figure out how this works. So what is the flux through that box? Let's look at the flux through that box. I'm going to go to a new page, which isn't quite so busy. So go ahead. What's the flux through the box? Right, the flux through the sides are 0, and then there's 2 ends. So the flux through the top end is just the flux through the top end is flux top is equal to E times A, and the flux through the bottom end is equal to E times A, right? The field is constant. The area is just A. The angle between the field and the area is 0 degrees. So it's EA cosine theta. Here, let's cosine theta, where theta is equal to 0 degrees, etc. So therefore, the total flux through the closed surface is equal to 2EA. That's what goes in here. The total flux through the closed surface is 2EA. Easy enough. Therefore, right, we're done. 2EA equals Q enclosed. Oops, nope, we're not done yet. Over epsilon 0. So 2EA equals Q enclosed over epsilon 0. We got to ask how much charge is enclosed in that box. The amount of charge enclosed in the box is equal to the charge density times the area, right? Let's go back. Well, we don't need to go back. Yeah, let's go back and look at how much charge is enclosed in that box. It's a part of the sheet that has an area A. The part of the sheet has an area A, and it's got a charge density sigma. So since sigma is equal to the charge enclosed over the area enclosed, therefore the charge enclosed must equal sigma times the area enclosed, which is just A. Okay. So therefore, Gauss's law tells us that 2EA equals sigma A over epsilon 0. And so therefore, E, the electric field due to the sheet, is equal to sigma over 2 epsilon 0. Make sure you understand that's the electric field above or below the sheet. That's the electric field above or below the sheet, right? Okay, so here's an interesting one. This is really a clicker question. Let's think about the situation. Instead of it being a flat sheet, right? The sheet, we didn't really talk about it, but it's an infinitesimally flat sheet. There was no volume to the sheet, but let's now talk about a volume. And let's make it a conductor. So I'm going to draw a picture. So now let's make a sheet that has volume. So it's really a three-dimensional rectangle, a book, I don't know, and put a charge density sigma on it. Now this is a conductor, right? Conductor. So the charge will go to all surfaces. Now let's make this infinitely large. So we're not worried about these sides, right? We're not worried about these sides because they go out to infinity. But there's now charge on the bottom and the top, right? So there's charge density on the bottom, sigma, charge density on the top, sigma. Whatever charge we've put on there, it goes to all surfaces. Now let's ask, what is the field outside of this conductor? What is the field outside of this conductor with a charge density sigma on its surface? So that's a clicker question. Well, actually, I haven't given you the answers. So there you go. There are your answers. You could pause the video and you could think about it and tell me what the electric field is above or below this conducting sheet, this three-dimensional conducting sheet. But I will go ahead and answer. The answer is, if I have done it correctly, is C, sigma over epsilon 0. I bet a lot of you probably answered the right answer, but I wonder if you really know why. And there's two ways of calculating this. What we can do is we can go ahead. So imagine a Gaussian surface, just our Gaussian rectangular box, put it in the surface and make the bottom of the Gaussian surface inside the conductor. The top is outside the conductor, the bottom is inside the conductor. We go to a two-dimensional picture. So this is the two-dimensional picture. So in this two-dimensional picture, the electric field lines coming off the surface, let me draw them in light blue. The electric field lines coming off the surface go through the top of our box, but there are no field lines in the bottom of the box. Why are there no field lines in the bottom of the box? There are no field lines in the bottom of the box because it's inside a conductor, and there is no field inside a conductor. So again, this is the picture, right, in 3 dimensions, and this is in 2 dimensions. And so when we apply Gauss's law, which is, again, the flux through the closed surface of the whole box is equal to the charge enclosed over epsilon 0, what you're going to find is that the flux is only through one end of the box, and so the flux, instead of being 2EA, is just E times A. The flux is E times A. The charge enclosed by the box is still the same, right? It's still sigma A over epsilon 0. So the charge enclosed is still sigma A, but the flux through the box is only E times A because the flux through the bottom of the box and the sides of the box is 0. So therefore, the electric field outside of this conducting, thick conducting sheet is sigma over epsilon 0. The other way you might have looked at this, I'm just going to draw right on top of this picture, is what if you chose a box like this? Again, it's got area on top and area on the bottom, right? So now there is flux through both the top and the bottom, right? And so now the total flux is indeed EA and EA. So therefore, the total flux, or integral of E dot dA for the big, ugly brown box is 2EA. But in this case, notice it is enclosing 2 surfaces with charge, right? It's enclosing 2 surfaces with charge. It has one surface with charge here and a second surface with charge here. So it's enclosing twice as much charge as the infinitely thin sheet. So therefore, let me find the right same ugly brown color. Therefore, 2EA is equal to twice the amount of charge, right? It's 2 times sigma A over epsilon 0. So therefore, E is equal to sigma over epsilon 0. So the field outside of a conducting sheet, is twice as much as the field outside of the infinitely thin sheet, which we never said was a conductor or not. But I guess we got to assume, I guess the easiest thing to say is that it's really an infinitely thin sheet versus a thick conducting sheet. Anyway, okay, there you go. Now, please keep in mind that when we use Gauss's law, it's a it's a scalar equation. There is no vectors that come out of this equation because it's a dot product, and so you need to know the direction. If I ask what is the field is sigma over epsilon 0. If it's a positively charged sheet, or a positively charged conducting sheet, the electric field points away from the sheet. And in the plus y direction or the minus y direction, if we were to define an axis, right, plus y. And if it's a negative sheet, it's going to point in the opposite direction, right? It's going to be towards the sheet. The electric field direction is towards the sheet if it's negative. And we've just been ignoring negatives a lot, so you just got to remember to pay attention to the sign of the charge and the direction of the field. Okay, so let's look at the back to the spherical symmetry. Let's look at a sphere of charge, but now let's, instead of doing a point of charge, we're talking about a sphere so that we can have charge in 3 dimensions instead of 1 dimension of a point. So here's my sphere. Let's make it a an insulating sphere. Let's start with an insulating sphere, and let's put a total charge density on this insulating sphere. I'm just trying to make it look spherical in 3 dimensions. And put a total charge density on it, in it, throughout it. Whoops. Let's just say it's got a constant charge density throughout, and the charge density is charge per unit volume, total charge over total volume. Now, this is not an infinitely large sphere, because then it would be not even spherical if it was infinitely large. And let's go ahead and make this a radius r, so that the charge per unit volume is q over, what's the volume of a sphere? 4/3 pi r cubed, in case we care. But let's just, we're given a charge density rho. And let's ask, what is the field due to the sphere? This is, let me write down. So it's an insulating sphere with constant charge density throughout. There's charge from the middle all the way out. If we want to know the field outside this sphere, we would draw our Gaussian surface around the sphere, right? Let's just go ahead and draw a Gaussian spherical surface around the sphere. And we will ask, what is the field at a distance little r from the center of the sphere, where r is bigger than r? E is equal to what at r, little r bigger than big R? So we would go through the whole process of saying, okay, we understand that this has a spherical symmetry. We're going to go ahead and apply Gauss's law to the dotted, the Gaussian surface, E dot dr equals charge enclosed over epsilon 0. And again, remember, what is given is the radius of the inner sphere and the charge density of the inner sphere. We haven't given you the charge of the inner sphere. Well, we sort of have, because you can go ahead and solve for the charge. Therefore, whoops, I guess I was sort of taken as a given, but the charge, therefore, if we're given rho and r, then you can find the charge is rho times the volume of the sphere, which is rho times 4/3 pi r cubed. So the charge of that sphere is rho times 4/3 pi r cubed, if it's got a charge density rho. Okay. Restating this, that's what's given, and we want to know this. So we're going to go ahead and apply Gauss's law, and E dot r, E dot dA is equal to charge enclosed over epsilon 0. And so therefore we can say same thing as a point charge, right? The electric field lines are going to be emanating off of this thing in a spherical way. Those are the electric field lines, and just like with a point charge, you're going to have E times the integral of dA of the through the Gaussian surface equals the charge enclosed by that surface over epsilon 0. The dot product goes away because the electric field lines are parallel to the area, the normal to the area, and the E is constant at a radius little r. And so the integral of dA is just the surface area of a sphere. So this is a surface area of a sphere. So this doesn't look any different than a point charge currently. So that E times the surface area of the sphere, 4 pi r squared, is equal to the charge enclosed over epsilon 0. I will take an aside here and note that you really do need to know the volume of a sphere is 4/3 pi r cubed, and the area of a surface area of a sphere is 4 pi r squared. If you have trouble remembering one of these, but you remember the other, do note that the surface area of the sphere is equal to the derivative of the volume with respect to r. That's a way that I do remember it, but that's not important here, really. You do need to know the volume and area of various basic shapes. Okay, so that's just an aside. Now let's go ahead and see what Gauss's law tells us. Remember, the charge enclosed was just Q, the charge of the whole sphere, so E times 4 pi r squared is equal to the charge enclosed, Q, over epsilon 0. So therefore E is equal to Q over 4 pi r squared epsilon 0. It's the same as for a point. I will note, though, that this is not really the correct answer because you weren't given Q. But it is the same as for a point. A sphere, outside of a sphere, it looks the same as a point. That's really important to understand. Outside of a sphere, spherically symmetric charge distribution, whether it's constantly, whether the charge density is constant or not, as long as it's a spherically symmetric charge distribution, a spherical charge density looks the same as a point charge. But this is not an appropriate answer because it's not in terms of the given quantities. Remember, the given quantities were rho and r, so the answer needs to be in terms of constants, rho and r. So therefore, E equals, oh dear, I did make an error here. Really important to note that we are talking about two different spheres. We're talking about the sphere of charge that has radius r, and the Gaussian sphere, which has radius little r. And this surface area here was the surface area of which one? Which one? Quick, which one? No, which that's the surface area of the Gaussian surface. That's the imaginary Gaussian surface. We're finding the flux through the Gaussian surface. So that should have been not big R, but little r. Gaussian surface. So that's not big R, but little r. These were just in general for a sphere. So this should be little r squared. And this should be little r squared. Let me rewrite it on another page. So that means the electric field is, the magnitude of the electric field was capital Q over 4 pi little r squared epsilon 0, a distance little r greater than big R. But that wasn't good enough because Q wasn't a given quantity. Remember that Q is equal to rho, and this is where it's important, is 4/3 pi big R cubed, right? It was given by the volume of the charged sphere, which is big R, and so therefore the electric field can be written as rho times 4/3 pi big R cubed over 4 pi little r squared epsilon 0. Simplifying that math, in terms of the radius of the sphere of charge for an arbitrary radius little r, the electric field is as follows. That's still just Q over 4 pi r squared epsilon 0. It's just we plugged in for what the charge Q was. So what is the electric field when R is equal to R? Whoops. Let's find a better color. I don't know if this is better. What is E at little r equals big R? At the surface of the charged sphere, what is the electric field? Well, we just plug in little r equals big R. So therefore, E is equal to rho r cubed over 3 r squared epsilon 0, right? We're plugging big R for little r, and so therefore that is rho r over 3 epsilon 0. Okay, let's do one more. What about for r less than big R? What about inside the sphere? What is the field inside the sphere? Ooh, green is a much better color. Those browns are really getting me down. So again, state the problem. We've got an insulating charged sphere with a charge density rho. There's charge throughout the sphere. And I want to know what is the electric field at a radius r inside the sphere. What is the electric field right there? Right? What is E right there? Okay? I'm just going to erase that. What do you think it is? Or how do you think you're going to find it? Think about that for a second. I would pause it and think about it for a second. Is the electric field equal to 0? Is the electric field equal to 0? Let's go ahead and draw a Gaussian surface. We'll still make it an ugly brown. Right? Our Gaussian surface is right here, and that's going to tell us, it's going to help us understand if the electric field at that little radius r is 0, because does the Gaussian surface enclose any charge? if it encloses charge, then there must be a flux through the surface. If there's a flux through the surface, there must be a field at the surface. And it does enclose charge because this is an insulating sphere with a constant charge density throughout. So it encloses charge. Since there's charge throughout, there's an electric field throughout this insulating sphere. Inside the insulating sphere, there's an electric field throughout. So let's go ahead and calculate what is E for little r less than big R. Well, that's easy enough to do, right? We're going to apply Gauss's law. E dot dA equals the charge enclosed over epsilon 0. And again, this is E dot dA on the left-hand side. It's the flux through some closed surface is equal to, on the right-hand side, the charge enclosed by that surface divided by epsilon 0. What surface are we talking about? We're talking about the imaginary Gaussian surface inside the sphere, the dotted brown line. I'm not going to draw any more arrows because it's going to mess up the picture, but we're talking about that the flux through the dotted brown line, which is a spherical surface inside the charged sphere, encloses charge, and it's got a flux through it. So what is that? Well, for the Gaussian surface that we draw on the dotted brown spherical shell, E, the electric field through it, it's still spherically symmetric so that it's constant, and it's still, the angle is still 0 between the electric field and the normal to the surface. So we're still going to have just E times the surface area of the brown sphere equals the charge enclosed by that brown sphere divided by epsilon 0. Or, as you know, the surface area of the brown sphere is going to be 4 pi little r squared. Don't confuse your r's like I did before. That's the surface area of the brown Gaussian sphere. So I've gone ahead and just made sure we understand. And it equals the charge enclosed by that sphere divided by epsilon 0. How much charge is enclosed by that sphere? I'm just going to write charge enclosed over epsilon 0 and say the hard part here, I don't know, the hardest part, because we've done all the other parts before multiple times. Oops, I forgot epsilon 0. Is the charge enclosed. How much charge is enclosed in that sphere? Think about that for a second. So we're going to find the charge enclosed by the Gaussian sphere by using the fact that we know that the charge density is the same everywhere and it's charge per unit volume. So therefore, the charge enclosed by the Gaussian sphere is going to be the charge density times the volume of the Gaussian sphere, right? The volume enclosed by the Gaussian sphere. The volume enclosed by the Gaussian sphere, whoops, wait a second. Okay, the charge enclosed by the Gaussian sphere is rho times the volume enclosed by this Gaussian sphere. So V enclosed is the volume enclosed by the Gaussian sphere. So therefore, the charge enclosed is equal to rho times 4/3 pi little r cubed. Because that's the volume of the Gaussian sphere, 4/3 pi little r cubed. So now we can go back and plug that into our Q enclosed, our red, here it's red, surrounded by the yellow highlighter. Now make sure we're looking at the left-hand side and the right-hand side. And now we've got little r's everywhere because big R really doesn't play a part in this. And so what we're left with is, from the other page, we had E times 4 pi r squared equals charge enclosed. I changed it from a little q to a big Q. I hope that's not a problem for you. It's still this charge enclosed equals rho times 4/3 pi little r cubed divided by epsilon 0. So now we just solve for the electric field. And so therefore the electric field is... Notice it's the same thing as when r was bigger than, little r was bigger than big R when we're outside of the sphere, but on top, the top was a big R, now it's a little r, right? Because now we're inside, so now the charge enclosed is enclosed by little r, not by big R. So that's the only difference. But what that ends up being is that ends up making a very different function. It's kind of interesting that the electric field is proportional to R. The electric field gets bigger as you move from the center out through this insulating sphere, But when you get outside the sphere, remember, it gets smaller as 1 over r squared. It looks like a point charge outside. So let's put it all together. So just rewriting what we found. We found that for inside the insulating sphere, the electric field goes as r. For outside the insulating sphere, it goes as 1 over r squared. Right? Big R is a constant, remember. Little r is the variable. And note that at little r equals big R, these two better be equal. You should be able to plug in little r and see that these two are equal to each other when little r equals big R, right at the surface. It better be continuous. It just says it's continuous, right? What I mean by that is let's make a graph. Let's go ahead and see what the electric field as a function of r looks like, right? At r equals 0, what's the electric field? At r equals 0, little r equals 0, what's the electric field, right? It's 0. Whoops, it's 0. And it increases radially. It increases with radius r. Until what? Until little r equals big R. And then what does it look like outside? It falls off as 1 over r squared. Whoops, falls off as 1 over r squared. So the field looks like that. So this is a graph of the electric field in an insulating sphere. In and outside an insulating sphere of constant charge density rho. Just showing that same thing again with the sphere in the picture, just to make sure we understand that the electric field gets bigger as we move towards the outside of the sphere, and then when we get outside the sphere, it gets smaller as 1 over r squared. Okay, that's all I got for today. That's pretty much all we're going to do with Gauss's law, I think. That's not true. Next class we'll probably talk a little bit more about it, but we'll move on soon to potentials.